It's currently thought that about 84% of matter in the universe is dark matter. And that's different to the kind of matter that you and I, the stars and planets, are made of. It doesn't interact with light at any energy, so we can't see it. And that's why it's called dark. But if we can't see it at all, how do we know it's there? The observations that led to the proposal of dark matter were made by Vera Rubin. Because dark matter has a mass, it affects the gravitational field. The stars and galaxies all rotate around the centre of the galaxy, in much the same way as the planets do around the Sun. The rotational speeds of stars and galaxies are not what is expected if all matter is of the normal type that we're used to. What we expect to see in galaxy rotation curves is that as you move away from the central bulge region of the galaxy, this region here, where most of the mass we can see is contained, that as you move away, there's a decrease in the rotational speeds of the stars. And this is because the force of gravity, which the central bulge region is exerting on the stars as they rotate around, is weaker the further away from the central bulge region you are. But what Vera Rubin found is that the actual curve looks more like this. So as you move away from the central bulge region, the rotational speeds of the stars remains roughly constant. And what this means is that there must be more mass that we can't see. So this is how we know that there's dark matter. Scientists have thought that there are two potential options for this dark matter. Machos, massive astrophysical compact halo objects, or WIMPs, weakly interacting massive particles. Machos are very faint objects like brown dwarfs, which are dead stars. And scientists have now found some machos, but nowhere near enough to explain all of the dark matter in the universe. So that means that dark matter must be made of WIMPs, a new type of particle. I asked PhD student Kate Dutson to tell me where we look for dark matter.
Dark matter, I mean, it's called dark because we can't see it, it's weakly interacting. So despite this fact, it does feel gravity. So it is massive, so it feels gravity. So we expect to find it more easily in the really dense regions of the universe. So wherever the everyday baryonic matter is dense, then the dark matter will be dense as well. Clusters of galaxies, for example, we think are bound by a dense dark matter halo, so they're a good place to look. And these are the largest gravitationally bound structures formed in the universe. Also, locally, like the centre of our galaxy is a good target because it's so nearby and it is a dense region of dark matter, in theory. The only problem with that is that there's a lot of contamination from galactic sources, so it's quite difficult to detect a signal there. So yeah, I mean, these are two popular targets: galaxy clusters, centre of the Milky Way. Also dwarf spheroidal galaxies, I think, because they're quite background free. So again, they're quite nearby. But then it's not as strong a signal. So there's kind of different targets, but there's different pros and cons for each one.
Okay. Understanding dark matter and its distribution is key to understanding the structure of the universe.
So the way that we think structure forms in the universe is hierarchically, so smaller systems merging to create larger ones, which leads to the clustering of galaxies. So all of this follows the dark matter because that's most of the mass. So this is why the kind of understanding that how dark matter clusters, halos and so forth will allow us to understand structure formation.
CTA might be able to detect dark matter through its annihilation or decay, because it's thought that gamma rays are released in this process, which the CTA would be able to detect.
Current observatories, so the Fermi Gamma Ray Space Telescope and the ground-based arrays that we've got at the minute, haven't detected a definitive signal yet. But CTA will be, an order of magnitude more sensitive than the instruments that we've got at the minute. So because of that, we might just detect a signal.